Now that we looked at how to use the voltage temperature coefficient to calculate operating voltage, we'll also learn how to use the percent temperature coefficient to perform similar calculations. Some specification sheets list the percent temperature coefficient instead of the voltage temperature coefficient. When this occurs, you'll see that the value is listed as a percent per degree Celsius. An example might be where a photovoltaic module has a percent temperature coefficient of negative 0.36% per degree Celsius. This means that for every degree change in temperature, the module's open circuit voltage, or maximum power voltage, will change in the opposite direction by 0.36%. We can take an example under cold conditions where a module has an open circuit voltage of 38.3 volts and a temperature coefficient of negative 0.36% per degree Celsius. First, we're going to subtract the STC 25 degrees Celsius from the temperature of interest, which is negative 20 degrees Celsius. We then multiply that value by negative 0.36% and we get positive 16.2%. If we add 16.2% to 100%, we get 116.2%. Finally, multiplying 116.2% by the original open circuit voltage at STC, which was 38.3 volts, we get 44.51 volts per module. Checking again, the module voltage under these conditions is higher than the original VOC because the temperature is colder than under STC conditions. Applying the same methods for warm temperature conditions, we have a module which has a maximum power voltage of 31 volts and an ambient temperature of 29 degrees Celsius outside. As we discussed before, the rooftop temperature is considered to be 30 degrees Celsius above the ambient temperature, which gives us 59 degrees Celsius. We subtract 25 degrees Celsius from 59 degrees Celsius and then multiply that value by negative 0.36% to give a negative percentage. Adding that product to 100% gives us only 87.76%. Multiplying that maximum power voltage of 31 volts gives us 27.2 volts per module, which is lower than the maximum power voltage at standard test conditions. So there are several ways to complete these calculations as they're relatively simple arithmetic, but the order of the coefficients does change. There may be another way that you find easier to use, such as removing the percentages or using just decimals. In either method that you use, just check that your answer makes sense once you get your final voltages. In the end, you should now be able to locate the absolute low temperature for a location using a weather resource, as well as determine the average high temperature for a location using a similar weather source. You should also know when to use those high and low temperatures to determine open circuit voltage or the maximum power voltage. Finally, you should be able to explain why it is important to calculate those operating voltages based on temperatures. In the next lesson, we'll learn how to calculate true insulation when there is shade involved in an array design.